Okay, so this is the robotic exoskeleton arm proof of concept video. We will, instead of using the muscle sensor, which is attached to my arm, we will be using a potentiometer to show the proof of concept with our design logic. So currently, the muscle sensor, which is the first two hex values, is at 0, and the flex is technically at its 0. And so as you can see, the motor is stabilized at the start position. As we increase the potentiometer, it will change the position of the arm until it reaches its area where the difference between the muscle sensor and the actual position are 0, and so it will maintain that position. The closer it is to that position, the slower it will go, which is why it's going pretty slow. So if we increase this a lot, if I could move this potentiometer, there we go. It moves fairly quickly up until its desired location, and then if we go all the way, it goes all the way to max, and the hard stops in this wheel keep it from going any further, preventing injury. If we lower the muscle sensor and our flex position is too high, it will force it down at a continuous rate. The rate's pretty slow right now because we have to assist the arm down because of friction. It won't just free fall. And so that's why we've decided to keep the number pretty slow right now. Yep, the next thing to show is that if we don't press the pressure sensor, this is simulating over 20 pounds, the motor just doesn't even move. And then to also show that our kill switch works, if we press the kill switch, the motor doesn't move. If we press the kill switch multiple times, it doesn't turn it back on. If we mess with any of the sensors, it won't work. We have effectively turned off the system at a base level, and the only way to reset it is to turn off and on the FPGA again, which we will show right here. There you go. Ready, set, let's go! Come on, what the heck happened?
It didn't work.
This is the exoskeleton arm team. My name is William Clarke. I am the mechanical engineer on this project.
I'm Anthony DeVore, electrical engineer. I worked mainly on control software.
I'm Rosalyn, also electrical engineer. I worked mostly with the hardware.
I'm Benji Smith. I worked a lot with I'm a computer engineer, and I worked a lot with the wiring and then also helping with the control logic.
So we're going to start with Will explaining the hardware.
For the overall purpose of the frame, we wanted to try and keep this as lightweight as possible. So for the frame, we decided to go with a PVC frame and an acrylic plate that's attached to it, so that it could be easily changed and adding components to it, but still strong and lightweight. So then we decided to go with a pulley system to amplify the strength because we needed to keep the cost down. This transfers out to the arm, where then on this elbow joint, it's attached here, it wraps around, so then the torque will be having a force applied right here at all times. And then the weight would be held here with the arm strapped in. And yeah, so this arm frame is made out of steel, and it is just really thin steel plate. And we have lots of holes in here to be able to allow for changing the size and shape to fit the user better. And same thing here, we have one for the arm. This can slide in and out to fit different sizes of arms. And that's about it for the physical components. And we're going to talk about sensors with Rosalyn.
Yeah. Awesome. So we'll kind of talk about the different mechanical systems that we needed to use. So our system is basically used off of 4 main sensors. So the main input sensor is the EMG sensor that's going to be attached right on the user's arm. Actually, I have to come in. this bad boy right here. So what this sends out is electromyography, so it senses how much someone is flexing their muscle. So as someone flexes more, it'll go closer to the maximum input voltage that we go, and as they are just relaxed, it'll go towards 0. As our main feedback sensor, we use this flex sensor that's located on the elbow joint of the arm, and it kind of slides just in and out of this little sleeve. And this is telling where the current position is. So the EMG input sensor tells where we want to go, and this is going to tell where we are. In addition, we also have this pressure sensor that's located on the arm, and this is mostly a safety feature, so the person can't lift more than 20 pounds, which is more than the system is rated for. We also have, if I can find it, somewhere in here. It's okay. We also have a kill switch located in here that if when they just push it, it'll immediately set the system down. It's okay.
Oh, it's tied into the straps right now.
And then that's kind of how the whole system works. All these work in conduction to turn the motor, and then you will talk about the wiring.
Okay, yeah. So we'll start off from the sensors since Rosalyn was just there. So the flex sensor is probably the easiest one to see, and we have just wire wrap done right at the sensor ends, and then we took, and on some of them we did a little bit of soldering to make sure it was extra secure, and then we put electrical tape around our wire wrap to turn them in basically into cables. And so we'd go from the sensors down to this breadboard, and this breadboard is basically just a place where we have an easier interface to be able to work in between the FPGA and then the sensors and to other locations. So this breadboard is kind of just an intermediate place for things wiring wise to be. So going from there, you'll go to the FPGA, and then also the FPGA goes over to the driver motor, the motor driver, and that is just one single ribbon cable, so that doesn't go over to the breadboard. And then we go from the motor driver all the way to the motor itself, of course. And then we have a little bit of solder work down here at the bottom because we need to have this in series because that gives us the most torque, and we found we needed more torque in this. And so at this point I think it's time for Anthony to talk about our control logic on the FPGA.
Okay, so control logic on the FPGA, it's quite a few simulations that you'll see in the report in MATLAB, and also the simulation in the model sim for the FPGA. If we scoot a little closer, we can start to see a little bit of the debugging that was, not debugging, but values that were used to control this. So we have 6 hexadecimal 7-segment displays, and we used those. These first 2 are the muscle sensor, and it's obviously not plugged in, so it goes to 0 volts. It's not letting any voltage through. The next one is the flex, and as you can see, as I move the flex, that number changes. And then the last one is the pressure sensor. So if I press down on the pressure sensor, that number goes down to 0, because that's how the pressure sensor works. All of these numbers worked in a conjoining control algorithm that changed the output PFM, pulse frequency modulator. That would go through the clock signal, which goes down into this driver, which will turn the motor. If at any point the EMG signal is less than the flex data, which I had to change from, it's I think it goes from 8.6 hex up to 9.6 hex. Around those values, I had to translate that to 0 to 5 volts. But if at any time the EMG muscle sensor was less than the current position, then it drives itself downwards since we don't have tricep control. And all that does is it flips the directional control on this stepper motor, and then it gives it a pre-described PFM value. So with that all together, you can see in our proof of concept video that this is our system.
So a couple of things I would improve on here. First of all, the pulley system. For right now, we have we have separate pulleys, but in other mechanisms, to be able to make this so that the forces, instead of being spread out, they would come in and be more linear, so you'd have a direct up and down. You could stack these on top of each other and create the multiple loops and get more force. Another mechanical thing would be we need to add in, instead of these eye bolts here, because these are catching when there's too much friction, we would want to change those out with flat pulleys that the wire could go through, and it would roll as it transfers the motion instead of trying to drag and cause a lot of friction. Then here on the structure, so because of lack of time, we had to make a 3D printed elbow joint, but in ideal, this whole system would be made out of a little bit of thicker material, so that it would be a little bit more rigid and strong. But then the forearm plate here, this would be welded to a metal elbow joint, so that it would be one unit and not have other residual forces in there. And then we'd also want to do a center of mass analysis on the arm to see where the actual rotating point of the elbow should be, so that it's not going to be fighting as much as it's trying to rotate. So then with all of this, those are the big things. Obviously there's little brackets and things that we could make a little bit nicer, and place the center of mass on the back to be able to be a little bit more evenly balanced. And then the last thing would be we wanted to have a mechanical system to account for the mass balancing. Obviously we didn't have that on here, but that would be something to integrate into the back of this as well, so that it could offset and keep the person upright, even if a weight is attached to the side and causes a bending moment. The weight could go over to the side and give them that straightening out.
Yeah, so during the course of this project, we ran into several issues. Some were hardware, some were control issues. One of the first issues that we found was some trouble with the AECs. We found that using integrated AECs can be difficult, but can be made to work. So we probably would have researched that out a little bit better going in, so we wouldn't have to waste so much time. We also found that we're having some conductivity issues. So if you'll notice, we went through here and we just insulated all of this arm with rubber to try to make it so that the user was completely isolated from the circuit. It worked okay, but it didn't work great. And as you saw in the videos, when we were using the potentiometer, it worked the best. And when we had the user completely isolated, it worked pretty good. Another thing that could have been easier is because because flexing your muscle is very difficult to keep a smooth, even voltage curve. I probably would have, going back and doing this again, I would have kind of put in a filter of that to make it a little bit more smooth. Using the potentiometer, it was really smooth. It was a nice, easy move of the motor, but when we're using the EMG, it was kind of jagged just because it's kind of a jagged signal coming in. We also had to change the battery, this bad boy, the day before this was due, because we accidentally, each one of the members of the group except one shorted it at some point, and then we accidentally left it plugged in all night. So it was dead by the time we got to it. So that was a fun expense. So we learned to be a little bit more careful with our batteries.
First place kind of started with me because we did start off not originally with the FPGA. That just ended up working better. We had started with a microcontroller and we had ran into problems with that. But one of the things I ran into while working on that specifically was that some of the documentation for that had not been the most clear. So one of the big things for me will be when I'm reading other people's documentation is to remember that they still make mistakes and that I need to watch out and make sure I understand them completely, because there were definitely a couple times it misled me and probably cost me a couple hours alone off that. So that is definitely one place I would first change things. The second is definitely getting off the breadboard sooner and getting to where we actually have the system where we had the wire wrap and all that stuff. Once we start getting all the things out there off the breadboard, I felt like it started coming together a lot faster and we started to understand things a little bit better. So getting the actual system built much sooner is something that I think would help everybody. Also just taking the time to think about some of these things that at the end we kind of neglected. Some of the things that got neglected worked out okay, such as the sleeve for the flex sensor. That worked out actually really amazing for how short notice we kind of put on that. But the support for the hand gave us some difficulties, and we still would like to improve it. So definitely more forethought, I think, is a lot of what I learned out of this in areas I hadn't thought about it as much in previous things I've worked on.
Okay, the things that I would have done differently is one, I would have actually argued for using a microcontroller FPGA combo. The main problem that I had writing this FPGA software are lookup tables. FPGAs can't do calculus, so I had to make lookup tables, and that is the worst thing in the entire universe. I think I spent 8 hours or more, no, I spent more than 8 hours just writing lookup tables. So I had nothing to do with the logic, it was just making sure that the values could be read. And I'm sure there's tricks of the trade that I don't know that can make FPGAs work better that way, but I would argue that we use the FPGA to collect the ADC data, because the ADC on the FPGA, even though it was really annoying, worked slightly better than the microprocessor FPGA because we eventually, microprocessor ADC, because eventually we got it working. So, but then I would argue that we would send the data that we get from the FPGA to the processor, have the processor do the math because it's built for that, and then it sends back data to the FPGA that would create the PFM signal. That would make it so much better. Yeah, other than that, everything else has been said, so. Flexing.
It's at E, 4, 3, 3.
Yep. It got stuck because friction.
Well, that's not good because we need to put a weight on it.
Yep.
So let's try it. Sorry, I'm in front of you. Let's try it with the weight. So.
What's going on, Rosalyn?
I don't know. It's just not pulling. It's trying. You want me to?
Yeah.
It's all good.
It will maintain! Okay, let's shut it off. On muscle sensor on. Relax the arm.
We're at E right now.
Am I still at E?
Are you relaxed?
I'm relaxed.
And now it's going. Now it's relaxed.
Okay, here's the next test. Flexing. And relaxed.
You're at about C. Okay, you're high.
We're still not isolated. Okay, we've added more rubber to try and isolate it, so here's the next test. Let's do this.
Improvement.
This is improvement.
It's close!
It's not as good as when you're isolated, but I would
Yeah.
say that's still mostly working.
So, the only reason that this is not fully working, as we described in the proof of concept video, is because I'm not completely isolated with the muscle sensor. But if I flex harder, it goes up.
And if you relax,
And I
it
relax.
should still go down.
We have a bit of friction. Is it trying to go down?
No,
Okay, well, I'm not isolated, so... Oh, now it's trying to go
no,
down.
it's trying to go down.
As soon as you
Whoa,
press
whoa,
the
whoa.
metal, it stops. I don't know why. Yeah.
Is it because I'm not grounded?
I don't know. So we have some isolation issues, but here's our next proof of concept video. We'll submit this with the EMG sensor isolated. Check it out! Okay, next test. We are isolating myself from the system. Hopefully that works better. Tell me when you're ready.
It's on. Go ahead.
Okay. We're at 0, which is good. Muscle sensor on. Flexing.
It's at E, 4, 3, 3.
Yep. It's working now. It's still going down pretty slowly though.
Time to replace anything?
Just for fun. Yeah.
For one, probably nicer pulleys.